The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so yesterday we learned about equations of planes and how to think of 3x3 linear systems in terms of intersections of planes and how to think about them geometrically. And that in particular led us to see in which cases actually we don't have a unique solution to the system, but maybe we have no solutions or infinitely many solutions because maybe the line of intersection of two of the planes happens to be parallel to the other plane. So today, well, we'll start by looking at equations of lines. And so in a way, it seems like something that we've already seen last time because we have seen that we can think of a line as the intersection of two planes. And we know what equations of planes look like. So we could describe a line by two equations telling us about the two planes that intersect on the line. That's not the most convenient way to think about a line usually, though, because when you have these two equations, how do you solve them? Well, okay, you can, but it takes a bit of effort. So instead, there's another representation of a line. So if you have a line in space, well, you can imagine maybe that you have a point on it, and that point is moving in time, and the line is the trajectory of a point as time varies. Okay, so think of a line as the trajectory of a moving point. And so when we think of the trajectory of a moving point, that's called a parametric equation. Okay, so we're going to learn about parametric equations of lines. So let's say, for example, that we are looking at the line through. So to specify a line in space, I can do that by giving you 2 points on the line, or by giving you a point and a vector parallel to the line, for example. So let's say I give you 2 points on the line, -1, 2, 2, and the other point will be, let's say, 1, 3, -1. So, okay, it's pretty good because we have 2 points on that line. Now, how do we find all the other points? Well, there are points in between these guys and also on either side. Let's imagine that we have a point that's moving on the line, and at time 0, it's here at q0. And in a unit time, I'm not telling you what the unit is. It could be a second, could be an hour, could be a year. At t equals 1, it's going to be at q1. And it moves at constant speed. So maybe at time 1/2, it's going to be here. Time 2, it will be over there. And in fact, that point didn't start here. Maybe it was, it's always been moving on that line. At time -2, it was down there. So let's say q of t is a moving point and at t equals 0, it's at q0. And let's say that it moves Well, we could make it move in any way we want, but probably the easiest to find, so our goal is going to find formulas for the position of this moving point in terms of t. And we'll use that to say, well, any point on the line is of this form where you have to plug in the correct value of t depending on when it's hit by the moving point. So perhaps it's easiest to do it if we make it move at constant speed. On the line, and that speed is chosen so that at time 1 it's at q1. So the question we want to answer is, what is the position at a time t, so the point q of t? Well, to answer that, we have an easy observation, which is that the vector from q0 to q of t is proportional to the vector from q0 to q1. And what's the proportionality factor here? Yeah, it's exactly t. At time 1, q0q is exactly the same. Okay, maybe I should draw another picture again. I have q0, I have q1, and after time t, I'm here at q of t, where this vector from q0 to q of t is actually going to be t times the vector q0, q1. So when t increases, it gets longer and longer. Okay. So does everybody see this now? Is that okay? Any questions about that? Yes?
Blue is pretty bad from up here.
Okay, so I will try to avoid using blue. Thanks for... that's fine. So, okay, I will not use blue anymore. Okay, well, for this time, let me just make everything white just for now. This is the vector from q0 to q of t. This is the point q of t. Okay, is it kind of visible now?
Yes.
Okay. Thanks. Thanks for pointing it out. I will switch to brighter colors. So, okay. So apart from that, I claim now we can find the position of this moving point. Because, well, this vector q0, q1, we can find from the coordinates of q0 and q1. So we just subtract the coordinates of q0 from those of q1. We'll get that vector q0, q1 is 2, 1, minus 3.